Okay, thank you. So, hello, I'm Taro Matsuo from the University of Osaka. So, first of all, I'd like to sincerely thank the organizers for giving this opportunity to share our latest work with the UNISEC global community. So today I will discuss how we can search for life on exoplanet and how CubeSat missions can contribute this ambitious goal. So my talk will mainly focus on the science case for direct imaging of exoplanets with future space telescopes. So I will briefly introduce the formation flying interferometry, especially why it is essential for exoplanet science. And then I will hand over the technical details to Professor Ikari-san. So, okay, so I would like to begin with this iconic image taken by Voyager 1 in 1990. So from about 60 million kilometers away from Earth. So inspired by this image, so Dr. Carl Sagan described Earth as a pale blue dot. So the color of the Earth has become a symbol of a life-bearing world. So my talk is to explore how this pale blue dot concept connects to our search for life in the universe. So let me briefly introduce myself. So for the past 15 years, I have worked in astrobiology, particularly at the intersection of astronomy and instrumentation. So my background is in high contrast optical systems for detecting exoplanet, and I worked on novel instruments at several NASA institutes. So currently, I'm working on a new formation flying interferometer program called Serios. So in collaboration with the University of Tokyo, led by Ikari-san. And this mission will launch in 2031, and then aims to demonstrate space interferometry for the first time. So anyway, let's go back to my topic. So since the first discovery of an exoplanet in 1995, more than 6,000 exoplanets have been confirmed. And then statistical analysis from the Kepler space mission show that approximately 30% of stars host at least one Earth-sized or super-Earth planet. So this means that potentially habitable planets are common in our galaxy. So therefore, the next big milestone in the field of astronomy is directly observing habitable planet candidates to look for the sign of life activity on the distant planet. So fortunately, two telescope concepts have been identified so far. So one is a visible coronagraph called Habitable Worlds Observatory, HWO, led by US community. And another is an infrared space interferometry called LIFE, so led by European community. I'm involved in both programs deeply. So however, the search for life on the distant planet is very, very challenging. So compared to the in situ measurement in the solar system, such as Mars and Europa. So one of the problems is that a distant planet cannot be spatially resolved by the telescope. So we just observe the planet as a point source, and only the information we obtain is a spectrum of the planet. So for example, as shown in the right panel, so Earth shines through the reflected light from the sun in visible, and then emits the thermal light in the mid-infrared. So this leads to the first major scientific question. So how can we identify life from a single unresolved point? So, and there is another difficulty. So detecting an exoplanet is often compared to observing a firefly next to the lighthouse. As shown in the left panel here, so the image taken by the Subaru telescope shows an exoplanet here, always embedded in very bright stellar light. And in addition, the planet is always very close to the host star on the sky. So that now we identify two key technical barriers. So extremely small angular separations of less than 0.1 arcsecond, and also extremely high contrast of 10 to the minus 10th in visible and 10 to the minus 7th in mid-infrared. So both high resolution, high spatial resolution, and high contrast are required simultaneously. So in summary, so there are mainly two challenges. So on search for life on exoplanet orbiting nearby stars. So one is, so how to identify life activity on the distant planet. And another is a technical challenge. So about how to detect a faint light from planet embedded in the bright stellar light. So I will mainly cover the first topic and briefly provide a technical pathway toward solving the second point. So first of all, so it is very difficult to directly observe the life itself on exoplanet. So we always observe the surface environment dominating the sign of life, even in life exists. So for example, red edge from higher plants, so which is a high reflectance of land plant due to the photosynthesis, so cannot be detected by future space telescopes because land plant is still localized and is embedded by the signal from the surface environment. So based on the previous Earth-shine observations. So however, life always interacts with the surface environment and alters the surface environment through their metabolisms. The altered environment could interact with the surface environment. The altered environment so could play as a selection pressure for life, so leading to the further evolution of living organisms, so which is called Darwinian evolution. So therefore, I'm particularly focusing on the co-evolutionary relationship between the Earth and life. So over the past 4 billion years, the surface environment of Earth have been altered by metabolism of life. And the environmental change could accelerate the evolution of life through the Darwinian evolution. So one of the representative examples, as you may know, about the coevolution of the Earth and life is the history of the oxygen concentration, so in the atmosphere. So one indicates the current oxygen level in the atmosphere. So the oxygen concentration has gradually increased over the past 3 giga-year. So especially after the first oxygenic phototrophs around 3.0 giga-year ago, so called cyanobacteria, emerged. So the surface water has been gradually oxidized, and then finally leading to the great oxidation event called GOE 2.4 giga-year ago. And this oxidation event is very, very important for both astrobiology and the evolution of life. So from perspective of the astrobiology, so the planetary scale environmental change may be helpful for remote detection of life activity on the distant planet. So this is because the signal is now enhanced and then is more easily detected even from a unresolved source. And also this global oxidation also promoted the birth of the aerobic respiration, and such as eukaryote and also multicellular organisms. So now I recall the parable dot concept introduced in the beginning of my talk. So this is because the color of the Earth might have been also changed by the life activity over the 4 giga year as an example of the coevolution of Earth and life. So of course, the blue color comes from the daily scattering of sunlight in the atmosphere and the absorption of sunlight by ocean. So however, I raise a big question. Was Earth always blue? So the reason why I raise this question is so Earth has been gradually oxidized by phototrophs through the 3 giga year. So as a result, so chemical compounds so generated in the atmosphere and also oceans through the redox reaction and could change the color of the ocean and also atmosphere. So, and leading to the color of the Earth. So one of the good examples is blue tide. So this picture was taken in Tokyo Bay. So blue tide is formed by colloidal sulfur, so which efficiently scatters blue and green light. So as you may know, human activities supply abundant nutrients to oceans and leading to an increase of the biomass. And then, so once dissolved oxygen in the water is consumed by living organisms, so the redox state of the ocean has changed. And then colloidal sulfur are generated through the redox reaction under the ocean. So that is one of the example for the relationship between the surface environment and life. So especially humans. So and now let's look back to the Archean era. So Archean era means so it's defined as the period between the 4 giga year and giga year ago and 2.5 giga year ago. So this area. So before the birth of the cyanobacteria, so the atmosphere and water environment were fully reduced, and indicating that so reduced iron was spread over the entire ocean because they are fully dissolved in water. So, and then probably the color of the ocean is of course blue, was blue. But once cyanobacteria emerged in the surface water, so they started releasing the oxygen to the surface waters, and then leading to the formation of iron hydroxide particles through the redox reaction. So because iron oxide efficiently absorbs the UV and blue light, so the light environment might be constrained to green light because the water is always absorbs the red light. So it means blue and red light can be absorbed by the iron hydroxide and water, and the green light remains under the water. And we expect that the color of the green light, the color of the light environment under the water could accelerate the evolution of the photosynthesis to absorb the green and orange light. So anyway, so we found now we performed a field experiment to validate this concept. So, and fortunately, so Japan is surrounded by the volcanic activities. So, and the one of the good examples is Io Island in Kyushu. So, where the hydrothermal vents exist. So, around the island, and the reduced iron is it's emitted and then released to the surface waters, and then of course the water is water has abundant oxygen, so the reduced iron quickly oxidizes to iron oxide, and then the color of the ocean could be also turned into green. And we, in fact, we performed a field experiment to measure the light environment under the water. And then we found that the green light environment actually exists and at the depth of the around 5.5 meters. And this concept now, so we could connect this concept to the evolution of life. But I will skip this point. But basically, the evolution of life, especially photosynthetic organisms, has been evolved with the surface environment through the 3-giga-year. And now we expand this concept to the search for life in the universe. So as shown in the left panel, the underwater light environment is also connected to the albedo of the oceans. So this is because iron oxide efficiently scatters the underwater light, so leading to the 10 times higher albedo than the normal blue oceans. So showing the blue line. And this is based on the remote sensing data. So in addition, the spectrum of the oceans has sharp edge around 550 nanometer due to the strong absorption of the blue light by iron oxide. So based on the geological record, so now we expect that green oceans would have lasted for at least 1 giga-year. And in summary, so green oceans provide the new framework for search for life on exoplanet based on the understanding of the coevolution relationship between the surface environment and especially life through the 4-giga-year. So that's all for the first topic. And then, so I quickly introduce the second point, especially the technical aspect for the search for life. So as I explained before, the faint planet light is always embedded in the brighter stellar light. So the exoplanet community has identified two telescope concepts, as we explained. And especially I focus on the latter concept, which is directly related to the lifelike mission. So first of all, I briefly explained the very basic concept for life. So life aims at the characterization of thermal emission from temperate habitable candidates. So, and then the number of habitable target is approximately 50. So the main object is detecting the biosignature gases, such as ozone and methane in the mid-infrared spectrum, ranging from the 5 micron to approximately 20 micron. And then also to increase the spatial resolution. So the baseline of the interferometer can be increased up to a few hundred meters. So, and of course, life also achieves the high contrast to observe the faint planet light embedded in the stellar light. So life consists of the nulling interferometry for high contrast, and also stellar interferometry for high spatial resolution at the same time. So the light panel shows the concept of the nulling interferometry. So basically, the phase of the phase of the one of the two beams is shifted by pi phase, and the two beams are combined to make a destructive interfere. So it's fringes for the stellar light. In contrast, planet light comes from the off-axis angle, so leading to the offset phase, adding to the one of the two phases. So the planet light is not perfectly null and can be separated from the host star. So that is a basic principle. So you can see you can understand for telescope for the life mission, but basically 2 telescopes for the nulling and 2 telescopes for the stellar interferometry. So. And I think I also need to emphasize the history of the space interferometry. So there existed more than 10 space interferometry concepts, so including the terrestrial planet finder interferometer, TPFY, so which is almost the same as a lifelike mission. So which was proposed in 1990s. So, however, all of them have been canceled in 2010. So now, lifelike mission has been identified by the European community. So now, NASA held 2 workshops at Caltech 2 times. So regarding the key issues on space interferometry, and also lunar interferometry. So we have identified several critical technologies, including formation flight. And among them, our main conclusion is to take stepwise approach towards the large space interferometry missions. So that is the last slide. So now we have launched the serious project to perform the technical demonstration of formation flight for the first time. And then there are 2 main objectives. So one is to demonstrate the millimeter level formation flight. And also another is to stabilize the fringes through controlling the optical path difference between the 2 beams from the daughter satellite with a precision of a few hundred nanometers. So thank you very much for your attention, and I would like to hand it over Ikari-san. So especially, he will talk about the technical detail of the series.